Hello and welcome to this lecture. In the previous lecture, we saw the notion of area under the curve with simple, speed versus time picture, giving a lot of, just for straight lines, how to do it and all that. We also saw the concept of integration, how to break up a big interval into smaller intervals to compute area under the curve in an easy manner. Now we are going to generalize that notion. Instead of just looking at straight lines, we'll assume an arbitrary function, some f of x, which is a function of x, some shape, any curve. How do you find area under that curve? And the crucial notion was to dividing it up into smaller intervals and then doing some bounds or some, assuming that the function is flat in that small interval, right? That was the crucial idea, right? When it is flat, you get a rectangle, you're able to find the area. So you assume the function is flat there. So such operation is called a Riemann sum. So this integral that we look at is called the Riemann integral, and that comes from this Riemann sum, and we'll see how to formally define it and how to compute it. So why should area under the curves be such an important thing? We already saw for distance, it goes from speed to distance, etc. But it can have so many other applications. Like for instance, you may be interested in finding the area of some types of shapes. Like for instance, the circular shape, right? The circle is very, very common. The circle is given by this formula, y equals square root of 1 minus x squared. Who does it come from? It's basically x squared plus y squared equals 1, right? Any point here is at a distance 1 from 0. So if you think of a x comma y here, x squared plus y squared should be equal to 1. So from there you get y equals square root of 1 minus x squared. So if I were to find the area under this curve from 0 to 1, I would have found the area of the circle, right? How do you find the area of the circle? By this method. So area under the curve can directly give you useful things like area of common shapes. That's number one. Number two is going from derivative of the quantity to the quantity itself. This is the example we saw, going from speed to distance, right? Derivative of a quantity to quantity itself. Here's just an illustration. If you have v of t equals x prime of t, which says distance derivative is speed, which is the derivative of position. Now v of t versus t may have any arbitrary curve. In the previous case, in the free falling object, we saw a straight line, but it turns out the free flowing object, because of air resistance, usually has a speed versus time which looks like this. It starts off accelerating and then it flattens out, and then it stops, almost goes at constant speed. Assuming wind resistance and all that, you can show this. So how do you compute distance now as a function of time? Right? How do you, there's a derivative here, and here also area under the curve helps you. So x of t is the area under the curve. How do you compute these areas, and all that we'll see later, but area under the curve is very, very useful for this purpose. Speed versus time is not the only thing that's related in a derivative fashion, right? We have in the circuits field, if you look at voltage across the capacitor and the current through the capacitor, that has a derivative relationship. And so many other derivative relationships are very, very common. So anytime in a physics experiment you want to measure a quantity, you also want to measure how that quantity varies with time. And that also has a name. Like for instance, work versus force or work versus energy, and all sorts of relationships are also variations with time. So it's not just with time, there's lots of other derivative relationships in economics, for instance, some demand versus supply and all these kind of things are there. So there's lots of derivative relationships out there. So it's not just in physics with respect to time. So many other areas always have a derivative relationship. So these derivatives are very interesting, and whenever you have to undo a derivative, you have to do area under the curve. So this notion of area under the curve being antiderivative is very, very, very useful. So stay with us as we embark on this journey of finding this how to do the area under the curve in an easy way. So here is a more general view of how to approximate area under a curve. So here is a general function f of x. It varies like this. Now it's not a straight line anymore. It varies like this, and I'm interested in area under this f of x from a to b. So this area, whatever the shape may be, the area below this from a to b. How do you approximate this? Our idea will be very similar to what we did for the speed versus time. I'm going to take this interval a comma b. I will divide it into n parts. This n will be some integer, 2, 4, 8, 16, whatever, 100, 200, 300, whatever number you want to take, and usually we are thinking it of as large number. I'm going to take this interval a, b and divide it into n parts. What will be the length of each part? That I'm going to call as delta. b minus a by n, right? That is the length of each part. So, the ith part will be a plus I delta to a plus I plus 1 delta, okay, for all I. Okay, so let me just show it to you for n equals 4. Okay, if n is 4, delta is going to be b minus a by 4, right? There are 4 parts here. Each part is of length delta. What will be the first part? A to a plus delta. What will be the second part? A plus delta to a plus 2 delta. What will be the third part? A plus 2 delta to a plus 3 delta. What will be the last part? A plus 3 delta to a plus 4 delta. What is a plus 4 delta? That is the same as b, right? Delta equals b minus a by 4. So, b is a plus 4 delta. That is the notion of dividing ab into n parts equally. Okay. So, the ith part is a plus I delta to a plus I plus 1 delta. Okay, I hope you saw this. This is easy enough to see, illustrated here for 4. Okay. So, we are going to approximate the area from A to B by first dividing it up into n parts, each of with delta, and I am going to make this delta very small so that my approximation becomes better, right? That is the idea, or n becomes larger and larger. So, AI, I am going to say, is the area under the curve in the ith part alone. Okay. Is that all right? So, area under the curve in the ith part. So, now ith part is a smaller interval. It is not A to B, it is a smaller interval, and hopefully in that smaller interval I can solve the area problem. If I can solve that, I can try to put it together for the overall area. That is the whole idea. Okay. Now, how do I approximate AI? Now, this AI itself I may not be able to find exactly, right? How will I be able to find it exactly? There is some variation in the curve. I won't be able to find exactly, but I will try to approximate it. Very similar to what we did in the speed versus time picture, right? How am I going to approximate it? I will be a little bit more systematic now. I will say xi is the midpoint of the ith part. Okay, what is the midpoint of the ith part? You add these two and divide by 2. You will get a plus I delta plus delta by 2, right? So, a plus I delta to a plus I plus 1 delta. The midpoint is a plus I delta plus delta by 2. So, that is the midpoint xi. Okay, xi has an explicit form like that. Okay, I will approximate the area AI as f of xi multiplied by delta. So, here I will do the rectangle approximation. Okay, so if you notice here, I have illustrated that here. In my first interval, I have x0. Okay, second interval, I have x1. Remember, I goes from 0 to n minus 1. In the first interval, I will look at f of x naught. That is the value here. I will assume, because I am thinking my interval is very small, right? My part is very small. So, I will assume that within that part, the function has a constant value of f of x naught. If I know it is a constant value, I know how to find area, right? It is just the area of the rectangle. So, it is just f of xi into delta. So, I will repeat that for each part. Notice, I am making some errors here, right? See, here is an area that I included which should not have been included. Here is an area that I have left out. Here is an area that has been included, should not have been included. So, outside the curve also I am including. Inside the curve, I am missing when I make this approximation. So, this is clearly an approximation. It is not exact, but still, as delta becomes smaller and smaller, I can hope that my approximation will become better and better. Okay. So, that is the whole idea, and anyway, most of the functions we consider will be continuous. And what do we know about continuous functions? When you come close together, the function will also be close together, right? When you come close to the x value, function will also be about f of x. So, this approximation may not be too bad, particularly for continuous functions. Okay. So, this is the core idea behind this approximation of area under the curve. Split a big interval into smaller parts, and within the part, assume that the function is roughly constant by taking xi as the midpoint. It turns out this midpoint choice is not too crucial. You can pick any other point also, right? Why should I pick midpoint? Maybe I will pick some other point, right? You could do that. It is not wrong. You can happily do it, but I am just illustrating with the midpoint. Okay. So, area under f of x from x equals a to x equals b, this whole area is actually a0 plus a1 till a n minus 1. This is approximately f of x0 into delta plus f of x1 into delta plus so on till f of xn minus 1 into delta. Okay. So, this is the crux to approximating area under a curve. Is that okay? Now, as I increase n, what happens to the approximation? Will it become actually the area under the curve is the question. It seems like it, right? If the function is continuous and nice, it should happen. and it turns out for most useful functions, all functions that you can think of that you will ever use, these things are true, right? As you divide it up, you can also intuitively see that this has to be true, right? So this will be true, and we can work with this kind of a Riemann sum, or this is called the Riemann sum, by the way. So we'll define that soon enough. This is a very, very important and easy way to approximate area under the curve. I hope this is clear to you. It's an important idea. Okay. So now, motivated by that important idea and approximation, we are going to define something called a Riemann sum. Okay, so this turns out to be an n regular Riemann sum. So this regular is because the parts are all of same length. The most general Riemann sum doesn't even require that, but we won't go to that. We'll just stick to regular Riemann sum. An n regular Riemann sum of a function f on an interval ab is basically what we saw before, this approximation of the area. Okay, delta is b minus a by n. And I have a vector x here. So this kind of notation is called a vector, okay, list of objects, x0, comma, xn, right? This is a list of objects. These are called vectors. Usually vectors have a bold notation. I will just see bold x here. Bold x is x0, comma, dot, 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 xn minus 1. So these are all points in the ith part, right? Xi is the point in the ith part. And what is my Riemann sum? Notice this notation here. This notation and all is sometimes a little bit troubling, but I hope you see why that notation is very simple and evocative and all that, right? So R is sort of a Riemann, N denotes this, how many parts I am dividing it into, this bold X denotes all the points I am picking in each of these parts, and F is the function for which I am computing the Riemann sum, A and B are the starting and ending point of the interval. In one succinct notation, I am capturing all of these things. And how do I define the Riemann sum? It is just that approximation of the area under the curve with the rectangle. You assume in the 0th part, function value is constant at f of x naught in delta, so on, so on, so on. So this is called a Riemann sum. Now, as I change n, I will get different values for the Riemann sum for a function. Okay, that's important. And as I increase n, I am hoping this will go towards the area under the curve. So that's the motivation for defining the Riemann sum. Okay. Now there are special cases. I may pick, just to illustrate how to pick these points, right? So these are called sampling points. I'll call this sampling points of the function. So the sampling points xi, I may pick in different ways. I may do a mid Riemann sum, where the xi becomes the midpoint of the interval. That's a plus I delta plus delta by 2. That's the midpoint, right? I may do a left Riemann sum, which is I take the left point of the interval, starting point, a plus I delta. I may do a right Riemann sum, which is a plus I plus 1 delta, the other point. All three I can do. In fact, or you can do anything, a plus I delta plus delta by 4 you can take, or 3 delta by 4. Anything you want you can take, right? Any point you want you can take there. But I'm going to illustrate with only these three. Okay? And it turns out it doesn't really matter. Okay? So you can pick any function, any point you like. Now the crucial thing is this Rnx of f comma a comma b is a sequence. It's a sequence in n, right? As I increase n, f and a and b are fixed, right? As I increase n, x will vary, isn't it? This vector x will vary. Sampling points will vary as I increase n. Do you see that? When I increase n, the number of parts become larger, so the number of sample points will become larger. Okay? So, but as I increase n, this will be a number only, right? This is just a number, Rnx of f of a comma b, and that you get a sequence. Okay? The question is, does it converge? Does this sequence converge? Right? We know sequences that don't converge also, right? So does this sequence converge? If it converges, then it might be interesting because that approximate area, may become the correct area. Okay? So let's illustrate. Okay, I'll show you an illustration. I'm going to pick a particular f of x, 2 plus 2x minus x squared plus 0.12x cube. Okay. Why did I pick it? It's a polynomial and it has a nice decent type shape. So I picked it. Okay. So I'm going to pick a equals 0, b equals 6. And I'm going to show it for n equals 1 to 20. Okay. Here is the mid Riemann sum. So this is the function. This red line is the function. Okay. Just why I told you I picked it for a good reason. It looks sort of nice. And a equals 0, b equals 6. And you can see I'm starting with n equals 1, 2, 3, 4, 5, 6. I'm starting with n equals 6. I'm not starting with n equals 1 here. N equals 6. And then I'll keep increasing that. Okay. So let me play this for you and show you how this works. So you see as n increases, look at what's happening to this area of the rectangle and compared to the area under the curve. See, the rectangle width is becoming smaller and smaller and smaller, tinier and tinier and tinier. This whole area is gently but surely approaching the area under the curve. right? So this happened for the midpoint. This is only an illustration with one function, but still you get the idea, right? Hopefully you get the idea. Here is the left Riemann sum. Okay, so you notice here I made the left point as the constant here, right? At the function it becomes constant, and again I've started with 6, and let us see what happens as n increases. Okay, notice here once again, slowly but surely, these rectangles are inching and inching closer and closer to that curve. Okay, isn't that wonderful? So you see here whether I picked a midpoint or left point, it doesn't really matter. And you can guess how the right will look. Okay, this is the right point approximation, and this one also, if I keep doing that, it keeps going and going and going and going and going. And there you go. You get there, right? So this is only till n equals 20, right? So if you do it doesn't quite look like n equals 20. I'm sorry. I think maybe my n is much larger here. I'll come and you can correct this. But anyway, it doesn't matter. n equals 1, 2, dot, dot, dot. Don't stop till 20. It goes on for a long time. Okay. If you let it go for a long time, you see that all these three areas, all these three Riemann sums, the mid Riemann sum, left Riemann sum, right Riemann sum for this function, they are all tending towards the area under the curve. Okay. So all three appear to converge to area under the curve for f of x from x equal to 0 to x equals 6. Okay, so this is again a central key idea in integration. You form these Riemann sums, approximate the area with the rectangle approximation, which is called the Riemann sum again. Then as you tend n to infinity, it appears that any Riemann sum is sort of converging towards the area that you want. Okay, so that's a nice thing to see. Okay. Alright, so let's do a few problems here. The problems are in computing Riemann sums. Okay, so here are a few functions and you have to compute Riemann sum for a equals 0, b equals 4 and n equals 5. Okay, so I'm going to show you for one or two functions just to show how it works. Let's pick very easy cases and slightly more complex cases. I will do Riemann sums very quickly for you. Okay, let's do Riemann sums. So the first problem is f of x equals 10. Okay, so f of x is 10. You can draw and visualize, but really that's not so important. I want a equals 0, b equals 4 and n equals 5. So what is delta? Delta is b minus a by n, that's 4 by 5. Okay, so it doesn't really matter what delta is, but anyway, it doesn't matter. So we'll do, it's asking you for mid Riemann sum, left Riemann sum, right Riemann sum, whatever. Let's say some xi you pick in the ith part, right? What will be f of xi? Whatever part you pick, what will be f of xi? It will just be 10 because it's a constant function, right? So what is my r 5x of f comma 0 comma 4? This would just be f of x0, which is 10, times delta, which is 4 by 5, plus again 10 times 4 by 5, right? So this is f of x0, this is f of x1, so on till n is 5. So you go up to n minus 1, isn't it? So you go 10 into 4 by 5 plus 10 into 4 by 5, 0, 1, 2, 3 and then 4. So you have 5 parts, 5 terms, all of them are 10. So what will the answer be? 10 into 4, which is 40. Okay. So for a constant function, this is really easy. There was another constant function that was given, f of x is minus 5. What will happen to minus 5? R 5x of f comma 0 comma 4, the same thing will happen, right? Minus 5 into 4, you will get minus 20. Okay. So we say area under the curve, but remember, if the curve goes negative, the area will also become negative. Okay, minus 5. So this area, well, usually we say area is positive. In the Riemann sum world, the area will become negative. Okay, because I'm just looking at f multiplied by the distance, and f is negative, the area sort of goes negative. So there's positive area and negative area depending on whether you're above the axis or below the axis. So that's one subtle difference, but it's still area, but can be positive or negative. Okay, so these two functions, ended up being very simple and very easy. Okay, let's take 2x, or we can take more complicated functions. It doesn't really matter what the function is. It's exactly similar to this. So you can take x squared plus x plus 1. Let's take x squared plus x plus 1. Okay, so your r 5x, I'll do the midpoint of f comma 0 comma 4. Oops, I think, did I make a mistake in the previous one? It's not, I think this is fine. Now I need f of x 0 plus, see the Riemann sum you can write like this, isn't it? F of x2, f of x3 plus f of x4 times delta, isn't it? And delta is always 4 by 5, isn't it? So because the delta is the constant, you can just pull it out and write it outside, and you only need to sum the function. Okay, and now what is this x0? You have to find, right? x0, x1, x2, x3, x4 you have to find. So maybe we can find that. X0 is going to be, it starts at a, right? So 0 plus the delta by 2 is 2 by 5. Okay, and then x1 is just 2 by 5 plus delta, so it will be 6 by 5. x2 will be 10 by 5, x3 will be 14 by 5, and x4 will be 18 by 5. Is that okay? So this is the x. So I have to put f of x0, so which means I have to find 2 by 5, right? So it will be 2 by 5 squared plus 2 by 5 plus 1 plus 6 by 5 squared plus 6 by 5 plus 1 plus 10 by 5 squared plus 10 by 5 plus 1 plus 14 by 5 squared plus 14 by 5, just writing very fast, plus 1 plus 18 by 5 squared plus 18 by 5 plus 1. Okay, whatever this value is, okay, I will let you calculate. There are maybe simpler ways to calculate this, but you will get this kind of value. Is that okay? I hope you see how that comes about. Okay, so we'll see later on maybe how to do it. There are cleverer ways to maybe add this up, but doesn't matter, you can just add it, you get the Riemann sum. Is that okay? Now hopefully you see for any other function f, how do you do the midpoint Riemann sum? You find the values, you find the delta, plug it in, you will get the answer. Is that okay? So I have to multiply, multiply by 4 by 5, I forgot that. Okay, I hope that's clear. Okay, so left, what will you do? For left points, x0 will be 0, x1 will be 4 by 5, x2 will be 8 by 5, so on. And for the right Riemann sum, x0 will be 4 by 5, x1 will be 8 by 5, so on. Okay, so you just have to plug it in and solve. Is that okay? I hope you see this. It's easy enough. I'm not going to do it for every possible case. For every function, it's just a question of evaluating that function. Sometimes it may be positive, sometimes it may be negative. You will get the answer. Okay? I hope this is good. Okay. So let's look at the second question. It says compute regular mid left Riemann right Riemann sums for the following functions: a equals 0, b equals 1, any n. Now any n, you have to be a little bit watchful. So let's do this any n, and the same x squared plus x plus 1 is there, right? So let's try that. This would be an illustrative sort of problem. So you have here f of x, let's say, is x squared plus x plus 1. Then a equals 0, b is 1, and any n, that means delta is b minus a by n, which is 1 by n, right? B minus a by n, 1 by n. Okay, and what will be xi? Xi will be a plus I delta. I'm going to do mid. Okay, for mid, xi will be a plus I delta plus delta by 2, isn't it? So that a is 0, I delta is I by n, plus delta by 2 is 1 by 2n. So it's just basically I plus 1 by 2 times 1 by n. Is that okay? Got that? I plus 1 by n times I plus 1 by 2 into 1 by n. Okay, you can also keep it as I plus 1 by 2 into delta if you like. Is that okay? So this is important. Find xi in terms of I. Okay, so this is an important step. Once you do that, everything is very easy. What is R n x of f comma 0 comma 1? It is just f of x0 plus f of x1 plus dot 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 f of x n minus 1 multiplied by delta, isn't it? So, it is just a summation. There is lots of sigma notation that people like to write. You can write like that also. So, I am going to teach you a little bit of that. So, this is going to be summation I equals 0 to n minus 1 f of xi delta. What is this sigma notation once again? For every I, you plug in every I here, and then sigma just stands for addition. Okay. So, you do I equals 0, you get f of x 0, plus I equals 1, f of x 1, like that. Okay. So, you loop over the values of I, and then sigma just tells you, you add f of x 0, f of x 1, like that. Okay. So, now xi is what? I plus 1 by 2 into delta. F is what? X squared plus x plus 1. So, this is nothing but summation I equals 0 to n minus 1 xi squared plus xi plus 1 times delta. This times delta will always be there. So, let me just evaluate this summation. So, what is xi squared? It will just be I plus 1 by 2 whole squared into delta squared, right? So, this will work out as, so let me just do I equals 0 to n minus 1 xi squared plus xi plus 1. It is good to get comfortable with the sigma notation a little bit. It will help you. Okay, it just conveniently captures the summation. Xi is I plus half delta squared plus I plus half delta plus 1. Okay, so now we have to add this. It looks a little difficult, but I'll give you a couple of formulae for this, and then it will become much easier. Okay, so let's simplify. Let's simplify this. Multiply it out. You're going to get here summation I equals 0 to n minus 1 I squared plus I plus 1 by 4 multiplied by delta squared plus I plus half multiplied by delta plus 1, isn't it? Should keep all this very carefully. Don't simplify ahead of time. Then you will have summation I equals 0 to n minus 1. You have I squared, collect all the terms together. You have I squared into delta squared plus I into delta squared plus delta plus 1 by 4 plus delta by 2 plus 1, isn't it? How did I collect this? Check this. 1 by 4 delta square, I'm sorry, delta squared by 4 plus delta by 2 plus 1, right? So, this delta squared multiplied each of these things, so you added all the constants terms together. Okay. Now, it turns out the sigma will go inside summation. You have summation sigma I squared plus I plus this, you are just adding, then further adding outside. So, you can push the sigma notation inside the summation, inside plus any summations that you have, not inside multiplication. Be careful about multiplication, but when you add, you can push the sigma inside. So, you have here, and delta square is a constant, right? Okay, so this will become I squared times delta squared plus summation I equals 0 to n minus 1 I times delta squared plus delta plus summation I equals 0 to n minus 1, just 1 multiplied by delta squared by 4 plus delta by 2 plus 1. Okay. So, this one from 0 to n minus 1 I am adding 1. So, I will just get n here. 0 to n minus 1 I am adding n. So, I will get n minus 1 into n by 2. 0 to n minus 1 I am adding I squared. Here there is a formula. You will get n minus 1 into n into 2 times n minus 1 plus 1 by 6. Okay, so this is a formula. So, these formulae you should know. What happens to summation from 0 to 1 to n minus 1 I squared, 0 to n minus 1 I, 0 to n minus 1 1. What happens to these things? So, this is the expression that you will get. Okay. So, n minus 1 into n into 2 times n minus 1 plus 1. Okay. So, this is this you might want to remember. I equals 1 to n of I is basically n into n plus 1 by 2. Okay. Summation I equals 1 to n I squared is n into n plus 1 into 2n plus 1 by 6. Okay. Summation I equals 1 to n I cubed is n into n plus 1 by 2 whole squared. Okay. So, these three you can commit to memory, and once you do this, you will get what you want, n minus 1 into n into all these things you will get. Is that okay? So remember delta is 1 by n, right? So remember that delta is also a function of n, it's not independent. Delta is 1 by n, and just for comfort I've left it there like that. Okay, and there's also overall delta multiplying this. So let's just clean this up, we'll simplify this, and then that would be good. Okay, so let's do that. So you get here n into n minus 1 into 2n minus 1 by 6 times delta squared. Okay, we'll keep all this, plus n into n minus 1 by 2 times delta squared plus delta, plus n into delta squared plus 4 delta by 2 plus 1. Okay, so this is my summation. Notice how the simplification worked. It's a little bit arduous, a little bit painful. I picked a slightly more complicated problem, but I've shown you in good detail how to go about doing it. Find xi in terms of I, okay, and then plug it into f of xi. You will get all the square, etc. I'll simplify, and then you will get the final form for the whole thing using these summation formulae. You have to be careful what the limits are, right? It may go from 0. Why doesn't 0 matter? I equals 0 is just 0, right? It doesn't matter. It's as good as I equals 1 to n minus 1, I equals 1 to n minus 1, I squared, and so on. Okay, but here the 0 matters. Okay, 0 to n minus 1 is as n, it's not n minus 1. Okay, so be careful about how this works. Okay, finally, my Rn x of f comma 0 comma 1 is going to be this whole thing multiplied by another delta, right? Remember, don't forget this other delta. This another delta is very important. This will change your answer significantly. Okay, so if I multiply by another delta, what will happen? I have n times n minus 1 2n minus 1 by 6 times delta power 3 n into n minus 1 by 2 delta power 3 plus delta squared plus n into delta power 3 by 2 plus delta squared by 2 plus delta. Okay, I hope you see this. Now let's plug in delta equals 1 by n. Okay, so this you have to plug in. If you do that, you will get 1 by n cubed. This one n will cancel here. So you get n minus 1 into 2n minus 1 by 6n squared plus n into n minus 1 by 2 into, so this n also will cancel here. You will get 1 by n squared plus 1 by n. Okay, plus n will also cancel here. You will get 1 by 4n squared plus 1 by 2n plus 1. Okay, so now this little bit more work to be done. Okay, now we can tend n to infinity, right? So if you tend n to infinity, what will happen? Limit as n tends to infinity, Rn x of f comma 0 comma 1 will become what here? So notice here, this if you want you can simplify. So limit as n tending to infinity. Let me simplify this. You get here 2n squared minus 3n plus 1 by 6n squared. Here you will get, you can do it differently. You can split this term into two parts. So you will get n minus 1 by 2n squared plus n minus 1 by 2n plus 1 by 4n squared plus 1 by 2n plus 1. Okay. So limit as n tending to infinity, here you know how to do this. This will just be the n squared will cancel here. All these other things will become small. So it just becomes 1 by 3. Here it will go off to 0. This will go out to 1 by 2. Here you will get a 1. So it's 1 plus 1 by 2 plus 1 by 3. You can simplify that if you like. It will be what? 2 by 6 plus 3 by 6 plus 6 by 6, 5 by 6, 11 by 6. I hope this is correct. 11 by 6. You can check this. Yeah, I think it's correct. 5 by 6 here, 11 by 6. Okay. So you see here, this Riemann sum and tending it to a limit took a little bit of work. Okay, I'm not saying it was very easy. It took a little bit of work, but it's not too difficult. It's just you have to be careful with the algebra. Some of you may be a little bit scared of the algebra, but that's okay. It's not so important. Soon enough, we'll find other ways of finding this limit. Okay, we will not have to do all these painful calculation to get to the 11 by 6. We'll quickly get to the 11 by 6 in some very easy way. Okay, for that you need to know rules of integration. We'll come to rules of integration soon enough. But before that, I hope you saw how this Riemann sum and its limit as n tending to infinity can be done very carefully with limits. Okay, I'll encourage you to do the other problems, x minus x cube. The other problems might be slightly easier. Go through this calculation. The reason to go to this calculation is to find out that it's a little bit painful, and then hopefully you will agree with me, you need better methods for computing Riemann sum, limits as n tending to infinity, and area under the curve. Okay, thank you very much.